Hello. In this video, we're going to have a look at the binomial theorem, but for powers that are not necessarily just whole numbers. So what we've already seen is that when n is a natural number, we can use this binomial expansion theorem, which uses combinatorics. So we have, for example, if I wanted to expand a plus b to the power of 3, this would be a cubed because that's 3 choose 0, a cubed times b to the power of 0. 3 choose 1 is 3, and then we've got a squared b to the power of 1. 3 choose 2 is also 3, and then a times b squared, and then 3 choose 3, which is 1, and we get a to the power of 0, b to the power of 3. So we can use that to expand a binomial when we have nice natural number exponents. But we can actually extend this for any rational power. So this includes negatives, it includes fractional powers. And it's a slightly more complicated formula, but you can see it here. And we're just going to have a look at what it is. We assume, for the sake of this particular formula, that the absolute value of the first term is greater than the absolute value of the second term. That doesn't change any generality here because we can certainly swap the order of those if we need to. So if I look at an example where I have 1 minus x to the power of negative 3, and we're saying here that the absolute value of x is less than 1, so that we meet that criteria of the first term being larger, the absolute value of the first term being larger than the absolute value of the second term. What this would look like if I'm writing the first 5 terms in the expansion. Well, the first part, a to the power of n, well, what I have is a equals 1. I have b is negative x. Our n is negative 3. And what we see actually repeated quite a lot in this formula is the b over a. So since a is 1, that's just going to be b in this case. So essentially what this formula requires us to do at the outset is factor out the a so that we have 1 plus b over a. So what we end up when we do this, well, a to the power of n is just going to be 1 to the power of negative 3, which is 1. So I can ignore that part of the formula and start with 1 plus n, which is negative 3, times b over a, which is negative x. That's my first term. Now, n times n minus 1, so negative 3 times negative 4, divided by 2 factorial, which is 2, times negative x now squared. The fourth term will be negative 3 times negative 4 times negative 5, divided by 3 factorial, which is 6, times negative x cubed. And the fifth term will then be negative 3 times negative 4 times negative 5 times negative 6, divided by 4 factorial, which is 24, and that will be times negative x to the power of 4. Once we simplify all this, what we end up with is 1 plus 3x plus, we're going to get 6x squared here, 10x squared or 10x cubed, for the fourth term, and 15x to the power of 4 for the fifth term. What's important to note here is that this is an infinite polynomial. So what we're actually getting with this is not something that's strictly equal, because there are an infinite number of terms here, and each term that I add will actually have an impact here. But what I have is a polynomial that roughly approximates that particular expansion where the absolute value of x is less than 1. So actually, let's look at a graph. What I have in red here, so the function graphed in red is y equals 1 minus x to the power of negative 3. And the function graphed in blue is that expansion, that polynomial expansion. So if I note that that polynomial expansion actually does a pretty good job of approximating in this particular region. And not much beyond it. Now, I had said that we had a qualifier that the absolute value of x was less than 1. So from here to here, 1 is going to be the vertical asymptote of that y equals 1 minus x to the power of negative 3, so it definitely can't go beyond that it would approximate. But essentially, the more terms I add to this polynomial, the closer it will approximate the y equals 1 minus x to the power of negative 3 in the marked interval. So that is one of the valuable things about this expansion, is it can allow us to find approximations of things that are maybe not so easy to find directly.